Good afternoon. I'm Robert Frush, Associate Dean at College of Engineering, and I would like to welcome you all to a continuation of our Celebration of Faculty Careers Colloquium. Today, Chip Blatchley is our speaker, celebrating his many years of service here at Purdue, which has actually been quite a few. I started here in '97 and got to know Chip right away, actually, when we started doing some things. I think I was first introduced with Ron Wukosh, actually, to Chip. And a couple of things I just thought I'd mention a little bit about Chip. So Chip actually is native of West Lafayette, so has been here most of his life, but then went away to University of California, Berkeley. And interesting enough, after his, he actually did his undergrad here at Purdue. I skipped that part, but then went on to Berkeley for his master's and PhD. And what I do find interesting, because I was actually at a meeting a while back of faculty where we had the award ceremony, and there's been so many faculty I've known that have gone to Berkeley, went out from Berkeley a little bit, and then they missed Berkeley so much they went back. So Chip, very glad that you decided to stay here. It was your hometown. So, his talk today is Water, Water Everywhere, and I'd like to again introduce Chip Blatchley.
Thank you, Robert. Okay, so when GS, right here, for those of you who don't know him, asked me to give this talk, I was really kind of, well, what do I talk about? And for me, the obvious answer is water, so I put it in the title twice, just to kind of emphasize it. And the word everywhere is up there for a couple of reasons. One, that water is going to be important pretty much everywhere we go, but also because a lot of what I'm going to talk about in this presentation is people that have influenced me, two of whom are sitting in the back of the room. I know they don't want to be, at least my wife doesn't want to be at the center of attention, but you are right now. Anyway, people that I've had the opportunity to interact with, some of whom are in the room right now, who come from just about everywhere and that do things that relate to water or that relate to me. So maybe another kind of question that I had was, in terms of what to present, is to consider, what sort of path have we all taken? We've all taken kind of a unique path, and I'm going to talk a little bit about that. And I'm going to do that by focusing on, to a large degree, people that have influenced my path, which is a little bit unique. And I'm going to do this more or less in chronological order. So with that in mind, I'm going to talk about my parents first. And one of the unusual things about me is that, as Robert said, I grew up in West Lafayette. Both my parents were professors at Purdue. So my mom was a professor. My mom's in the middle here with a student in the School of Nursing. She's there giving a scholarship that's in her name in the School of Nursing. They do that every year. And one of the things that she did during her career was that she wrote a book that was published in 2 editions with a colleague of hers, Mary Lou Holy, on the topic of leadership and management in nursing. So I've illustrated a cover of that book there. My father, who's pictured over on the left, was on the cover of the Faculty and Staff Handbook in 1979 and 80. I have a copy of that at home just for fun. He was a professor in aviation technology. He taught aviation maintenance. And Bob, you might appreciate this. What he did in his class, which was really kind of his pride and joy, was work with students to completely disassemble a plane that was somehow in disrepair, and then they would rebuild it from the ground up and put it in flying order. And this was, in a very real sense, a service learning class before that term even existed, in the sense that there was a very real deliverable. One of those deliverables is right there. And my father delivered, he flew that plane to the Wright-Patterson Air Force Base, where it's been on display since the early 60s when his class rebuilt it, which I think says something about the confidence that he had in his teaching and his students' ability to rebuild a plane, that he would fly it. That's the only plane of its kind in the world that's left. It's a Curtiss P-6E, only one that's left. And he was the last person to fly it. So anyway, my parents were very supportive of me. They were there when I graduated from Purdue with a bachelor's degree in civil engineering. This was many moons ago. I'll let you guys just kind of figure out how long ago that was. Sadly, my father became ill not too long after this picture was taken. He died about a year later. He was a profound influence on my life, and I still miss him. Another influence on my life is sitting at the back of the room in the middle, where she doesn't usually sit. So she's now turning red, I'm sure. My wife, we met at Purdue. We graduated the same day in different disciplines at Purdue. We just recently celebrated our 30th anniversary. We're looking forward to the next 30. We're going on a great trip this summer to Alaska, where neither of us has been before. That picture was taken on the north shore of Maui. We've been to all sorts of interesting places together, and I really enjoyed that. So among other people that influenced me at Purdue that I want to recognize are some emeritus professors. And I've picked these kind of grainy images from the website that lists our emeritus faculty. We might want to see if we can update these things and see if we can come up with less grainy images. Most of the people up here were professors at Purdue when I was an undergraduate, and they all influenced me in a very positive way. They all challenged me. They got me to do things that I wasn't entirely convinced that I was able to do. They pushed me. I didn't necessarily appreciate it at the time, but I do now. And so maybe the message there is that students, when a professor pushes you, or somebody in a position like a professor pushes you, you should recognize that they're doing it because they care, and that they want you to do the best that you're able to do. One of the people that's illustrated here is Bill Wood on the bottom row. He was not a professor here when I was a student. He was a professor here when I became a professor. And he was not only a friend and a colleague, but he was really my mentor until he unexpectedly died on my daughter's 3rd birthday, which was 17 years ago. Very sad day in that respect. It was a great day for my daughter because it was her 3rd birthday, but kind of a day of mixed emotions for me because I lost a good friend and a mentor. When I was at Purdue, I had the pleasure also of learning how to row, and I participated in rowing for actually many years after I graduated from Purdue. And it was a great learning experience for me, so there's lessons here. You can learn a lot outside of the classroom or the lab also. And I learned a lot in this sport about not only who I am, but also how to work with other people. Rowing is the ultimate team sport. Much of what I learned related to rowing and team activities is because of this guy, Kevin Sauer, who was my coach all 4 years at Purdue. He since has gone on to start the program in women's rowing at the University of Virginia, which is always in the top 3 in the country. And he's been recognized by his peers as one of the best coaches in the country. And I really was fortunate to have him as an influence in my life. When I went to the University of California, my advisor was Jerry Thomas. He's hooding me here at the PhD commencement. Another person who was on my committee, and frankly that I spent more time with than my advisor, was the guy on the right, who's Christian Doughton. He may be the best technical writer I've ever met. I know that's a high standard to put out there because I know a lot of people who write really well, especially in the technical area. But he taught me the importance of attention to detail and really how to write, and for that matter, how to conduct experiments and conduct research. He was really, and still is, a gifted scientist. He doesn't publish very much, but what he does publish has impact, and here's just an illustration. This is a title of a paper that he and Thomas Turnus published 15 years ago. It's the foundational paper on the topic of how pharmaceuticals behave in the environment. And when I looked it up just the other day, it had 2,637 citations. I suspect that number has changed maybe a little bit since I looked it up, higher, obviously. But the point is that he writes papers that have impact. He doesn't write very many, but what he does write are incredibly well written, very detailed, and they're just almost pieces of art, the way that he puts them together. So that's a pretty high standard to meet in publication, but also one that's worth going after. Picture on the left is a picture that my wife took on my first day of work, and I think I still have that tie, although I don't think I'm going to wear it unless I get invited to a Halloween party or something. But and then we have had the pleasure of raising 3 wonderful children, one of whom is sitting next to my wife in the back, and I'm going to embarrass her. So we had the opportunity to go on sabbatical to Paris. This was in 1995 and 96, and it was an incredible experience, I think, for all of us, although I don't know how much of it Megan remembers. She was pretty small at the time. Anyway, so as I said, we've raised 3 children, and they're illustrated in adult form here in this picture. So I want to talk a little bit about them and also about the roots that my family has at Purdue, which are deep. So I've already mentioned that my wife and I both got our bachelor's degrees here, my wife in Krannert and me in civil engineering. My oldest son, the big one in the middle, is Tim, standing next to me. He has his bachelor's degree in mechanical engineering here. He's about to complete his master's degree in mechanical engineering here. But he's doing this while working at Ford in Dearborn, and he actually has a really cool job up there where he's working on energy management in hybrid and electric cars, and it's really, I think he really likes his job. Michael, my second son, the one over on the right, got his bachelor's degree in biomedical engineering in May, and he recently started in the PhD program at Johns Hopkins. And Megan, The one who's in the picture on my right, to your left as you look at it here, is a sophomore in the College of Education. She's, as John Fricker pointed out, she's known for a long time that she's wanted to be an elementary school teacher, and we need more people like her. I couldn't be more proud of her. So,
Haven't changed your mind yet? Okay.
so that's my family. Other people that I've had the opportunity to work with since being at Purdue include a number of my students. I've picked kind of randomly 9 of them here. I'll talk about several others as I go through this presentation. The top row is people who are working in non-academic positions, and they work not only all over the world, but all over the map in terms of their professions. So I have, for example, John Thompson, who has a really interesting position at the Department of State. He basically influences U.S. environmental policy, well, on behalf of the State Department and the U.S. Government. Dimitri Margatas works in Geneva. Bill Weaver works in Madison, Wisconsin for a consulting firm. Bruce Hunt, who was my first PhD student, is a senior vice president at a prominent consulting firm in Maine. The 4 on the bottom happen to have academic positions at a number of different institutions, and they're all doing really well. So I'm really proud of these students and proud to have had the opportunity to work with them. All right, so as an outline, I've already talked as much as I'm going to about who I am, and I want to talk a little bit about what I perceive to be some current and future problems that relate to water, which is kind of the focal point of this talk, and specifically about water treatment, which is what we do in my group. I'll also discuss a few needs and opportunities, and then maybe close with some random thoughts that are from the left field bleacher seats. But anyway, all right, so kind of the poster child for water problems, at least in North America, I think, is the city of Las Vegas. So these are a couple pictures that were provided by the Southern Nevada Water Authority, who provides water for the city of Las Vegas. Las Vegas, if you haven't been there, is a large, rapidly growing city in the middle of a desert, and they don't have very much water. And the water that they have is diminishing in quantity. From 2000 to 2010, you can see that the water level in Lake Mead went down considerably, and just for perspective, that's about 120 feet downward that the water went. And if you consider the surface area that's occupied by Lake Mead, you can, obviously that's a lot of water that they don't have now that they used to have. That has implications for them and many other people who live in the southwest part of the United States, not only in terms of access to water, but also in terms of access to electrical power, because Hoover Dam is used also to generate electrical power. So you can see that they're missing a huge resource that they had not too long ago, and it hasn't really improved much since 2010. So Las Vegas has done all sorts of interesting things with respect to water and trying to improve their situation with respect to water. One of which is that they recognize that the 2 intakes that they did have and still do have they were being approached by the surface level in Lake Mead. So they're currently in the process of drilling what they're calling intake number 3, which will be about 100 feet deeper in the lake, so that when the water level drops down to the level of intakes 1 and 2, they won't lose water, they won't go dry, which would have pretty serious implications for a town the size, well, any town, but especially a town the size of Las Vegas. So they've done a lot of things also to recognize the water quality that they have to deal with. And I've used this slide, I'm not going to go through the details of it, but really just use this slide to illustrate the fact that we do use water that's been used by people before us. And that will always be the case, it always has been the case. But I think what's going to happen in the future is that we're going to have to start using sources of water that we wouldn't have considered using before. So really what that means is that water reuse, it has always been taking place, whether we recognized it or not, but it's going to become more important. It's going to become more direct, widespread and intentional. It's going to require proper management, and it's also going to imply that we're going to start to use more marginal water in the future, waters that we wouldn't have used before. So water treatment is going to play a role. So what we do in my group is really kind of summarized on this slide, both in text and in some of the images that I'll go through. So we spent a lot of time working on disinfection processes. Much of what we do in my group relates to UV disinfection. And in that area, we've really spent a lot of our time focusing on what I'll call photochemical reactor theory. We spent a lot of time looking at the kinetics of disinfection and the chemistry that takes place in these disinfection processes. We've developed some analytical and diagnostic methods, a few of which I'll talk about, Currently, we're working on swimming pool chemistry, which we got into kind of because it was kind of fun and because there was some money available. But it turns out that what we've discovered in this setting also has implications in many other settings. And so we're exploring this in a lot more detail than we were, at least originally. And we're also doing some work related to water in developing countries. So I'll touch on each of these things, but just go through them very quickly. So with respect to photochemical reactors, when we started working on this, pretty much when I started at Purdue 26 years ago, the approaches that were used to try to predict the behavior of photochemical reactors were really very crude, and in part because they didn't recognize the importance of transport behavior. So one of my early PhD students did some really fundamental work that laid kind of the groundwork for the establishment of photochemical reactor theory, and she focused on examining, quantifying transport behavior in these systems. So it may not be easy to see, it's not a very good picture, I'm the photographer, but in this picture there's a physical model of a UV disinfection system that's in this flume that's in the hydromechanics lab. And what's this device that you can just barely see is a laser probe that's imparting 2 pairs of laser beams onto a spot within the system. And using a technique called laser Doppler velocimetry, it's possible to non-invasively measure velocity at a point. So you don't interfere with the flow field by conducting this measurement, and it allows you to conduct detailed measurements, including characterization of the turbulence characteristics of the flow field. So here's a data set that was developed from this method, and just to kind of walk you through it, each one of these little lines on here is an arrow that has both a length and a direction that illustrate the magnitude, the average of the magnitude of velocity and the direction of velocity at the tail of each one of these things. Each one of those little arrows took about an hour to measure. So you can see this data set took a long time to generate. The person who did this was, again, one of the first PhD students in my group, Kwangping Chu, who now works for MWH in Singapore. She really did a wonderful job of not only collecting that data, but then developing a model that allowed us to interrogate that data, simulate the trajectories of particles through that particular system, and then map onto those trajectories what's called the irradiance field that allowed us to calculate the dose of radiation. So I've used this tool not only in research but also in teaching, because it really is the fundamental tool for describing the behavior of these systems, and several of the students in this room have used this tool themselves. And one of the things that comes from this is that we start to recognize that the dose of radiation, here indicated by both a number and a unit, the dose of radiation that's delivered to a particle depends on the trajectory that that particle takes through a system. And you can see that the doses that are delivered to the 4 particle trajectories that are simulated here are vastly different. And that leads us to this thing. This was the first so-called dose distribution that describes the behavior of a photochemical reactor. Since then, there are many others that have been developed using other methods, some of which I'll talk about in just a second. But by using, or by being able to define this dose distribution, we're then able to predict the behavior of a reactor using this equation that I'm not going to bore you with. But the bottom line is that by knowing the dose distribution, which is this thing up here, and by measuring photochemical kinetics, we can use those 2 pieces of information to very accurately predict the performance of a photochemical reactor. And this is really a discovery that Kwangping made in her work. And again, it's allowed us to really kind of establish this as the foundation of photochemical reactor theory. It also allowed us to identify some weaknesses in the characteristics of the reactors that we were exploring. And by identifying those weaknesses, we were able to modify the geometry of those reactors and improve their performance by just simply changing the geometry of the wall and restricting access to the kind of low irradiance areas within the photochemical reactor. So we got a patent for that, and these reactors are actually being built and sold, and they have been for the last 15 years or so based on this approach. Now, one of the strengths of that approach is that it really focuses on the fluid mechanics within the reactor, but one of the weaknesses is it took just about forever for Kwangping to be able to do that characterization, and that was only at one hydraulic condition. So she did that at the time because that was really the only tool that was available to characterize fluid mechanics, but since then other tools have become available, for example, computational fluid dynamics. So CFD has emerged as a computational tool along with the computational hardware that allows people to do simulations that otherwise would have taken months to complete in the lab as experiments. So I'll just walk you through quickly how this is done. This is just slight exaggeration in terms of how long it takes to do this. So we'll first draw a picture of the reactor on the computer, and then we'll digitize that. And then, I shouldn't say we, then one of my students will run a simulation to represent on this computational grid the equations of motion and continuity along with an appropriate turbulence closure model so that we can describe the turbulent flow field within this system. One of the first students to do this in my group, and actually one of the first people overall to do this, was Zorana Nonovic, who is from Serbia originally. Just as an aside, when she finished her PhD, she accepted a position in Boston with Camp Dresser and McKee. She worked there for a few years and then more recently was moved back to Serbia, where she accepted a faculty position in civil engineering at the University of Belgrade. And she's doing a great job there. One of the things that she's done since getting back to Serbia is that she wrote the first book on the topic of environmental engineering in the Serbian language. It's the only one that exists now, and she wrote it. So she's another person that I'm really proud of. So here's some of her simulations. So for that particular reactor that I described there, which is a pretty simple reactor, she simulated the flow field. Once that was done, she could simulate particle trajectories, map onto those trajectories the irradiance field, and then calculate the dose that's delivered to a particle that follows that trajectory. And she can do that not just once, but for many trajectories, and then build the dose distribution. Once we have the dose distribution, then we can accurately predict the behavior of the reactor. And that approach is something that she also used in a method that we call numerical prototyping. This was some work that we did for NASA. They approached us and had an interest in having us develop a system to treat water on long-term space missions, so we did. They, for whatever reason, I still don't understand this, but they perceived that on a space mission, an unacceptable risk would be to have a mercury lamp on board. By the way, in this room, there's lots of mercury lamps. They're up here, and we don't really necessarily think about them as a source of risk. But for a long-term space mission, NASA has decided that mercury is not acceptable, so they wanted some other source of radiation. So we developed this reactor numerically using this prototyping approach where you build the reactor on the computer, you test it on a computer, you identify its strengths and weaknesses, then you try to fix them, you improve the geometry of the reactor, for example, and what we closed on through this iterative numerical prototyping approach is this reactor, which we ultimately built and tested and demonstrated for NASA to be a very efficient reactor that will satisfy their objectives. So this approach of numerical prototyping is something that now is kind of the standard for the construction, the design of UV reactors. So one of the leaders in this area is Trojan Technologies. And the student that I mentioned before, Kwangping Chu, I remember vividly when she gave a presentation at a meeting about the work that she had done using LDV. She was just barely able to step off the stage before she was ambushed by this company and offered a job. And she did some of the work that was instrumental in the design of this particular reactor using this numerical prototyping approach. So they use that also for the design of some other reactors. This is just a series of slides that illustrate the largest UV reactor in the world and the largest UV system in the world when it was being built for the city of New York. It's now online, and it's used to treat something like 2 billion gallons of water a day. It serves water or provides water for something like 9 million people in the city of New York. So it's nice that this technique is being used, and it's being used by a lot of people. So we have an inherent mistrust for computational models or models of any form. So we like to have experiments to back this up. So we've also developed some methods that allow us to measure the performance of these systems rather than just relying on numerical models to predict their behavior. And the kind of foundational method that we've used is the method of chemical actinometry that we call Lagrangian actinometry. So let me just first describe what a chemical actinometer is, and basically to paraphrase this, it's a chemical that does react photochemically where we know the mechanism, we know the products, we know the kinetics, and that allows us to use a measurement of a change in that chemical to measure how much radiation is being delivered. Now the difference in the method that we've applied is that we're going to apply this to a moving target. That's why we use the word Lagrangian in there. So the actinometer that we've used is something that we developed in conjunction with Don Bergstrom and his group in medicinal chemistry. And it's based on this compound on the left, which is related to one of the kind of building blocks of DNA. And it turns out that it reacts very similarly to UV radiation, as does DNA, which is nice because DNA is the primary target for UV radiation in disinfection applications. So what's perhaps useful about this reaction is that it takes this parent compound, which is non-fluorescent, goes through this intermediate, which then spontaneously decays to this product, which is very stable and brightly fluorescent. So we can differentiate the parent compound from the intermediate and the final product by this optical measurement. And what we do then, and I should point out also that the quantum yield for this reaction is close to 1, which is the theoretical upper limit, at least for a pure photochemical reaction. So it's very efficient, this reaction. And what we've done is to link, actually, before I talk about what we've done, I want to talk about the person who did a lot of this work, Chengyu Shen. So Shen got his PhD in 2005, I think, or something like that, and he was the one who was, you can see there was a paper that he was the first author on that was published in Environmental Science and Technology that really described the development of this particular compound as a chemical actin ometer. And since then, he's gone on to work for this company called HDR, and he runs a validation center that I'll show you pictures of in just a couple minutes. Anyway, what we did, also in conjunction with Don Bergstrom and Paul Robinson, who has faculty appointments in several groups, is to link this compound, here is our cytidine derivative out here, to the surface of a microsphere by first biotinylating the compound. That basically means we stick this biotin group on one end, and then we purchase streptavidin-coated microspheres, and we take advantage of the fact that biotin and streptavidin have a really high affinity for each other. They form a bond that has close to covalent bond strength, and that allows us to link that molecule to the surface of the particle, but to have some space between the surface of the particle and the photochemically active part of things. And that's necessary because otherwise we found that the surface of the particle will quench the fluorescence. So we do that a lot. We link a whole bunch of these things to the surface of a particle. And then we use this method, which is also patented, to actually measure the performance of a reactor. So the basic idea is we're going to choose microspheres that are similar in size and specific gravity to microorganisms. That means they follow trajectories through the reactor that are very similar to the trajectories that microorganisms follow. That means the dose that they receive is also going to be similar. And because we've linked this UV-sensitive chromophore to the surface of the microspheres, that means we can measure a change in fluorescence for these microspheres and relate that to the dose of radiation that's been delivered to the microsphere. So we measure that in large populations of these microspheres by imposing a large population on a reactor, collecting them downstream of the reactor, separating them, the microspheres, from water, and then aspirating those into a flow cytometer where we can measure at a rate of about 10,000 particles per minute. So when we do this, along with a little bit of math that I've skipped over, well, actually a lot of math that I've skipped over, we can measure a dose distribution. The black line on this graph is a cumulative representation of a dose distribution. The red line is what was predicted by the model. And these are really the only two methods that are available to either estimate or measure a dose distribution. And what's perhaps more important is that when we took those dose distributions and then integrating them with the kinetics of various reactions that we explored, they very accurately described the performance of the reactor. So we did that at very small scale, then we've done that at very large scale. So I mentioned a little while ago, Shen is running this facility. He's pretty much in charge of this. There are 2 of these facilities in North America. There are 4 in the world, and this is the largest of them. It has the greatest capability, in part because he's there. So here is Shen kind of directing the show with let's say the largest part of this system, which has the ability to deliver up to 65 million gallons a day at a flow rate, or as a flow rate, for a short period of time. So we've used this method to characterize this reactor, which happens to be the reactor that's installed at New York now. And here's just kind of an image of the completed system that's now running in New York. And the implication, or the importance of this with respect to the city of New York and why they care about this, is summarized here. I'm not going to go through all these numbers. I'm going to get right to the bottom line. In a drinking water application of UV disinfection, you must validate. So there are 2 methods that are available, one that's called biodosimetry, which is kind of a standard old kind of method, and the method that we've developed called Lagrangian actinometry. The difference between them really is the amount of information that those methods provide you about the reactor. Lagrangian actinometry provides a lot more information about the reactor than biodosimetry does. And the bottom line there is that you can greatly reduce a factor of safety in design. And the reason that maybe New York might care about this is that their system operates at 2 times that flow rate, 2 billion gallons per day. If their system was only 1 million gallons per day, they would be saving something like $500,000 a year in electrical power costs. But because their system is operating at 2 billion gallons per day, they save something like $1 million a year in operating costs because they validated the reactor using this method. So you can imagine there's other utilities that might have an interest in this. So we're pursuing that. Okay, we do also work with chemical disinfection. A lot of what we do with chemical disinfection relates to chlorine. Chlorine's used a lot. It's used in drinking water and swimming pools and municipal wastewater and reuse applications. And there's a lot of benefits and drawbacks that are pretty well known with regard to chlorine. One is that people know how to do this. We've been doing it for a long time. Philadelphia implemented chlorination about 100 years. In fact, this is the 100th anniversary of Philadelphia implementing chlorination for their drinking water supply. So chlorine is very effective against bacteria and viruses. It's not very effective against protozoa, and that's one of the big drawbacks of using chlorine. But what we've focused on is really the chemistry of disinfection byproduct formation, and that's really what I'm going to talk about briefly here. So one of the first students in my group who worked on this was Qi Shang. There's a picture of him right here. He worked on this method called membrane introduction mass spectrometry. We adopted this method from the work that Graham Cooks and his group in chemistry had developed to really kind of implement this method for a number of different applications. Our focus was on the chemistry of disinfection, especially around chlorine, although we've used it for other applications as well. So there's a number of characteristics of MIMS that I've listed over here that provide huge advantages for us analytically, and that for those reasons and others, we use this as a workhorse. We use it every day in my lab to do measurements of water chemistry because of those characteristics that are listed over there. So Qi recently was promoted to professor at the Hong Kong University of Science and Technology, and we keep citing each other's papers because we work in very closely related areas. Another person that has done a lot of work with MIMS is Jing Li, and I don't think Jing is here today. Jing has followed an interesting path also. Jing did a postdoc with me and left in 2009, I think, and was here for a few years before that doing this postdoc. And then she accepted a faculty position at the China Agricultural University in the Department of Chemistry. That's in Beijing. Thankfully, just recently, she was awarded a scholarship from the China Scholarship Council that allowed her to come back to Purdue, and she's back working in my lab for about a year. I'm really happy to have her back because she's not only a really pleasant person to be around, she's a gifted chemist. So it's great to have her. In fact, I think it was the first paper that she published in my group was featured on the cover of Environmental Science and Technology, which was kind of cool, I thought. And I was really happy for her. More recently, we published a paper together on the reactions between chlorine and uric acid. This turns out to be a really important reaction in swimming pools. I'll let you figure out why. But that reaction is important for a number of reasons, not the least of which is that we know that cyanogen chloride is generated as a result of reactions between chlorine and uric acid. So the American Chemical Society publishes a whole bunch of journals, and periodically they pick topics or articles from those journals to feature in their news releases. For whatever reason, they chose to feature this one as one of 4 articles from the total collection of ACS journals about a month ago. And in the last month, there have been articles or publications or presentations presented in a whole bunch of different media that relate directly to this article. And I was told, although I'm not going to feature it up here, that this was also discussed, if that might be a generous description, on the Bob and Tom show not too long ago. But I didn't put it up here for obvious reasons. Anyway, so in her work, Jing was able to use MIMS and information from the literature to develop mechanisms to describe, for example, the reaction between chlorine and creatinine, or chlorine and this amino acid, histidine, and we've learned a lot more about the chemistry of these reactions that take place not just in swimming pools, but in many other settings where these forms of organic nitrogen tend to encounter chlorine. Okay, we've also done some work to look at combinations of UV and chlorine, so we've done work in both of those areas, and it turns out that there's reasons to use them together. First of all, they're complementary as disinfectants. Chlorine's very effective against bacteria and viruses. UV is very effective against bacteria and protozoa. Put them together, you pretty much take care of every microbial pathogen that we care about. They're also effective when we use them together as oxidants. So we've discovered that halogens have the ability to activate some molecules and make them respond to UV radiation more favorably than they would have otherwise, and that allows us to open up some reaction pathways that wouldn't have been available to us otherwise. In turn, that's allowed us to target specific chemicals that might be of concern, like pharmaceuticals, in the environment. And we've also discovered that there are both constructive and destructive ways that these two things can be used together. So as an illustration of constructive applications of UV and a halogen, I'm going to just briefly describe some of the work that was done by Kelly Pennell, who recently accepted a faculty position at the University of Kentucky. Kelly worked with Zorana Nanovic. This is a paper that they published together. They were kind of the dynamic duo when they were here. Great people to work with. So Kelly's work included experiments that involved applications of iodide and iodate as a chemical actinometer to allow us to measure how much radiation is being delivered to a system in real time. So one of the interesting things about this is that the product of this reaction is this interesting ion up here, triiodide, from which we can actually generate active iodine as a disinfectant. So we can generate a chemical disinfectant using this method that we also use to measure how much UV is being delivered. So this was done as part of this NASA project, and what Kelly did in her work also was to explore how UV and iodine can be used together, and she discovered that they're not just additive, but in fact synergistic in terms of how they function as disinfectants, and NASA was pretty interested in that for obvious reasons. In terms of destruction, we also look at UV for breaking down various compounds. And most of what we look at are chloramines because they turn out to be pretty active when it comes to UV. So kind of the first work that we did here was to look at degradation of the inorganic chloramines, which are the simplest chloramine compounds. And we know from this work how fast they decay as a function of exposure to these various wavelengths. We also know what's formed as a result of that decay as a function of pH. And we also have a pretty good idea of what the mechanism is, and that mechanism proceeds or is initiated by the cleavage of this nitrogen-chlorine bond to yield an ammoniyl radical, which in turn opens up some reaction pathways that wouldn't have been available to us otherwise. And interestingly, I thought this was kind of fun, we form nitrous oxide as a product down here, laughing gas. So it's kind of fun to be working with that in the lab if you can. So another student who is here, she's there, who's working on a project at a high school that you might recognize, but that I won't describe for you. You can ask me about it later because I can't mention it in public, although it might be obvious for those of you who are locals. Anyway, Mernaz, who's in the back, is doing work at this unnamed high school on an experiment to evaluate the effects of UV on water and air quality in a chlorinated indoor swimming pool. And one of the things about her, I'll show some of her data in just a second, but one of the things about her work that I think is really interesting and pretty cool, frankly, is that she's had the opportunity to work with 25 AP chemistry students from this particular school. And for each of those students, I believe it's fair to say this is their first experience in research. So Mernaz has served as the mentor for these 25 students. I think all the students from years 1 and 2 are now in college, is that right? And the students in year 3, well, they're still there. And they're mostly, I think, seniors in high school. Anyway, I think it's just really nice that she's had the opportunity to be a mentor to those 25 young researchers. Here's some of her data that describes kind of the response of trichloramine, nitrogen trichloride, to exposure to UV. Everything to the left of this green line is before a UV system was installed. Everything to the right is after. There are some differences that show up in these data. It would take a while to kind of untangle this. We're still working on that. Trichloramine, by the way, is the chemical that you smell when you're around a chlorinated pool. It's not chlorine, it's that compound. And we know that that compound is important because it's been associated with asthma and a number of other respiratory problems, irritation of your eyes, irritation of your skin. It's just something you just don't want to have around. So being able to control that is potentially interesting. Another, I should say, former student who's sitting right back there, Shiqi Wang, who's currently a lecturer in the School of Civil Engineering. He finished his PhD in May? Was it May? August-ish? Okay, whatever. Sometime last year or so that he finished, and he's since been a lecturer in the School of Civil Engineering. He's taught 2 courses from us, done an excellent job. And more recently, he's, in fact, just within the last couple days, he's accepted a position, is that right, just in the last couple days? Accepted a position at Johns Hopkins in the School of Public Health. And I should point out there's maybe an interesting opportunity for us to pursue here. The position that he's taking is one that is in a collaboration between Hopkins and Montgomery Watson Harza. MWH is a big consulting firm in the environmental engineering field. They do a lot with water. The Hopkins School of Public Health also does a lot with water. And that sort of combination, I think, is something that represents an intriguing possibility that maybe Purdue ought to be thinking about as well. Anyway, so Shichi's work has involved several of the compounds that are illustrated up here and how they react when we use UV and chlorine together on them. And without going through all of the data that he's generated, and he's generated a boatload, here are kind of some of the central conclusions. When these compounds, amine compounds, are exposed to chlorine, then there's going to be chlorine substitution. That's what activates these compounds toward UV radiation, and it allows us to open up these reaction pathways that wouldn't have been open to us before. Again, that allows us to target some of these compounds and figure out ways to break them down in water. And it turns out that there's some other functional groups that display some of this interesting behavior as well. They're activated by chlorine. So here's an example. This is a compound, acetaminophen, this one right here, that most of you are familiar with. That's the active ingredient in pain relievers like Tylenol. When that compound is exposed, a lot of this is excreted, by the way. When you take Tylenol, a lot of it you excrete in human urine. So it ends up in our water supplies, whether we like it or not, and it's going to be chlorinated. So when that compound is chlorinated, there's some work that was published about 8 years ago by a group at NIST who identified a couple different products of this chlorination process. One of which is this one over here that I'm going to focus on in just a second. It's a quinone compound. Now I've added to this slide just some information about the toxicity of these things, and basically as you go from left to right, these compounds are becoming more toxic. So we care about these things in our water supplies. And just for purposes of illustration, here's a couple slides to illustrate differences in the behavior of these compounds. Acetaminophen itself degrades very slowly. It was exposed to UV radiation for 60 minutes, and that was a dose of about 700 millijoules per square centimeter, which will become more relevant on the next slide. The bottom line is that this is a chemical that degrades very slowly. It actually absorbs radiation pretty strongly, but that radiation is used very inefficiently in this reaction. On the other hand, when we look at the product from chlorination, this quinone compound, it reacts very quickly. On the previous slide, we had a dose of about 700 millijoules per square centimeter. Here we have a dose of 20, and we're getting like 70% decay. So the result of this is that this is a compound that absorbs more strongly than the parent compound and uses that absorbed energy much more efficiently, and because of that, it decays pretty quickly. So this is kind of an interesting discovery, and it allows us, again, to target potentially some interesting compounds that are present in water. So I'll spend just a couple more minutes talking about things that we do in my group, and the rest of what I'm going to talk about, at least in terms of research, relates to this topic of water in developing countries. I put a whole bunch of statistics up here just to kind of illustrate the importance of this topic. I think it's pretty clear. This is important. And this is a picture I took on a trip that I took to Uganda in 2009. I think that was what those people were drinking. There's no treatment involved. The treatment was carry it to your home in a jerry can. So, you know, this is reality for a lot of people, a significant fraction of the world's population. So there's many people, in fact, on campus, there's many people here at Purdue who recognize the importance of this, and many groups that are working on it. But off campus, there's also a number of prominent organizations that recognize the importance of this issue. For example, the UN or NAE, they've both identified this as a really important issue. And we know how to do this. We know how to treat water. Even in a developing country, we know how to treat water. So among the things that you need to do in a developing country are use locally available resources. So if you look globally at where the majority of people are who lack access to safe water, most of them live close to the equator. That's just the reality. So one of the resources that's going to be available to them is solar radiation. So we're not the first to kind of recognize this. This is, we can take advantage of this resource and treat water. So we're doing that. So we've developed a couple systems to allow us to treat water. The thing that I'm holding here with Paul Shen, who's actually a graduate student in electrical engineering at Stanford, he came to my lab last summer and we did some experiments to investigate the use of a Fresnel lens to focus radiation on this little tiny reactor here to treat water. And it turns out that works. And I'm not going to go through all the details of that because we don't have time. Another reactor type that we're using involves what's called a compound parabolic collector. This is a device that allows us to focus radiation in by a different pathway, but again allows us to focus solar radiation and then use that radiation to treat water. So the way that we designed the CPC, this was designed on a computer using this numerical prototyping approach that I talked about before. So here is the numerical prototyping result. That translated into a design and a construction, which happened to follow the same approach that I used to build this kayak. And the student who designed this thing, Uric Gentil Mbanimpa, he has an interesting story himself. He's originally from Rwanda. He then did a master's degree at the University of Missouri, and then he came to Purdue to do a PhD. This was the subject of his PhD. So the work that I'm describing here is really Eric's work and then the work of a couple other students. He's currently a postdoc in South Dakota working on climate change issues. So this is the work that was done actually after Uric graduated, but this was done by another student to describe kind of the relationship between the DNA-weighted UV dose and the response of E. coli. And from this, we've learned that the dominant mechanism of damage, inactivation of microorganisms, is damage to DNA, and that yields some promise with respect to the application of this for inactivation of other organisms. I had the pleasure of working with an undergrad to do this work. His name's Brian Vadheim. He was here on an REU program from actually Montana State University. Soon after he completed this work and some other work that I'll show on the next slide, he applied for and received a Marshall Scholarship, which is really a big deal. I mean, these things are about as competitive as Rhodes Scholarships, and it allowed him to study economics at the London School of Economics, where he is right now. Really cool person and a lot of fun to work with. So Brian's work and the work of others allowed us to identify the wavelengths of radiation that get the work done for us when we do this sort of thing outdoors. And that's illustrated here as an effectiveness spectrum or series of effectiveness spectra. And what we learned from this is that the wavelengths that we care about are between 300 and 310 nanometers. And that provides us guidance in terms of the materials that we're going to use for the development of these solar UV systems. They have to be compatible with those wavelengths of radiation. All right, last topic is a class. It's a service learning class that a group of us are teaching from 6 academic units: civil, environmental, nursing, ag econ, biology, and food science. I think I got all 6 of them. And interspersed among these people, who are mostly residents of a community called Las Canas in the Dominican Republic, are a bunch of, if you look carefully, you'll see a few scary faces back there, professors, and a whole bunch of happy faces, the students, that are involved in this class. And this has been a really fun class to work on. What we've been doing is meeting with people from the community of Las Canas who we were introduced to. I should mention actually before I go on to that, this is a presentation that the class gave at an EPA competition last spring in Washington, D.C. But again, we've been working with a community to identify this school, which is the Ana Julia School in Las Canas, as the location where we're going to build this community scale water treatment system. We were introduced to them by people that we know through Rotary and an organization that I work with called Aqua Clara International. We, on one of our trips down there, did water testing. We collected water samples. We worked with the school to do educational modules to teach them the importance of hand washing and proper sanitation. If you have clean water but dirty hands, doesn't matter how clean the water is, you're still going to get sick. So part of this program is to look really kind of holistically at the other issues that are going to affect illness. And then this is the system that we plan to build in the next couple weeks in Las Canas to treat their water and actually to provide a business opportunity down there for someone to run this and sell water to the community. All right, random thoughts. So what I do for fun is ride a bike, mostly. I do some other things for fun as well. So I like to go on long bike rides. So this is a picture that I took. It allows me to get to pretty cool places like this. Sadly, I was following somebody who was wearing an IU jersey, but okay, whatever. So I just put this up here because it's the best picture that I've taken recently on a bike ride. But on another bike ride that I did not too long after this one, actually, I figuratively bumped into a guy that was wearing a Purdue jersey. So I came up to him and started talking to him about Purdue. And the first thing out of, this was in the fall, first thing out of his mouth was complaints about how poorly our football team was doing. And that really bothered me because in the rest of our conversation, I discovered that this guy is a graduate of our aeronautical engineering program. And I I don't know, just as a kind of geeky person that I am, I would have expected that to be, especially when he discovered what I do, that would have been the first thing that he would have talked about. But no, the first thing that he talked about was football. And what bothers me about that is that I think that the marketing strategy that our university and most other large universities are using is really kind of misguided. I mean, it's great. If the football team wins, I'm happy for them. And even if the basketball team wins, although that doesn't happen very often either. But these things have become, I think, the identity for a university. This is an academic institution. It's not an athletic college. So, well, that's obviously clear. But anyway, but I don't think that should be our identity. I think we should be looking at other teams of people. So I put together my own football team, or a group of 11. These are faculty that I've had the opportunity to collaborate with. Not all of them. I mean, these are all faculty, but there's not a complete list of faculty that I've had the opportunity to collaborate with. Great people, they do great things. Their focus is on academics. Now, they could play football. I think they would not do very well. They probably would be bruised largely, but they would probably end up with a similar record to the Purdue football team in the end. But if you were to look at them as kind of a marketing ploy or a group that you would focus on for purposes of marketing the university, I guess my suggestion is not only would you not more consistently see high-end performance, but I think it would be also more consistent with what the university ought to be about. And I would just suggest that the university ought to consider focusing on people like this, maybe perhaps more than we focus on athletics. I mean, I think athletics is really great, but it should not be the focus of a university. All right, so I'll conclude just with some comments about what I plan to do in the future. My understanding is we're supposed to do this nominally every 7 years. So I'm going to lay down some things for me to accomplish, and you guys need to hold me accountable to this. So I have been doing research at the intersection of traditional disciplines, and I plan to continue to do that because I think it's really cool. So this is my view of where I am and those traditional disciplines. So I mean, I put myself at the center. That's kind of human nature, I suppose. But what's maybe more important about the location of engineering here is that there are intersections with many disciplines. And these are disciplines where at least I see opportunities for intersection between what I do and what I know about the work that people in other areas do. So I think there's a lot of opportunities there. And frankly, I think those are where the cool things are to explore. I hope to be able to write as many as 3 books, the first of which is Photochemical Reactor Theory. I've written the outline. I just haven't figured out when I'm going to write the book. And the others are relating to classes that I teach. And then the last goal that I put down here is more of a personal goal that I shared with my wife not too long ago. I want to ride century rides in all 50 states. I've only done 5 so far. This is one of them that I did in the state of Washington several years ago. So I have 45 more states to cover. So you need to hold me accountable for that. But I won't get them all done in 7 years. Anyway, so I'll conclude by thanking the members of my group, some of whom are illustrated up here, and the organizations that have funded my research. I think I got most of them, and thank you.
Well, I think we have time for some questions.
Chip, general question, not with your UV, etc. I hear a lot of talk about we're running out of potable drinking water. That's my own feeling. I cannot back up, but that maybe we have water, but is the distribution is the issue. That we may not have water exactly where we need it. And so, if that's the case, is there some cost-effective way of managing the water or getting the water where it's available and taking it to where it's needed?
I've heard some interest. So I suppose is the answer to that question, but I'm going to present a couple perspectives on that. So I heard Pat Mulroy, who runs or is in charge of the Southern Nevada Water Authority, is a really interesting, she's a great speaker. She speaks without slides and will captivate you. So if you ever get a chance to listen to her, do it. Anyway, I've been to a couple meetings where she has talked, and she suggested that the western United States ought to start mining water from the Great Lakes, build a pipeline. Personally, I think that'd be a terrible idea because I think it has potentially really important negative implications for the Great Lakes themselves. But anyway, that suggestion has been made. Another suggestion that we might consider is where do we put people rather than where do we put water. So, building a city like Las Vegas, or for that matter, Los Angeles or San Diego, in the middle of a desert, doesn't really make that much sense. And we might want to think in the future about where we encourage people to move based on access not just to water, but other resources that we depend on. And that might be another strategy we might consider. So, but what you're suggesting may be part of the equation as well. But I think the last suggestion should be part of the equation as also. I'm not sure if I answered your question.
I have one question. Many countries need water. Israel, for example, they use reverse osmosis engineering to turn seawater into drinking water. As an engineer, do you have any other solution, not only purifying water, but changing seawater into drinking water? That may be very useful in Africa or Las Vegas, anywhere.
Yeah, I mean, the problem with technologies like RO, or for that matter, any desalination process, is that you have this thermodynamic barrier to overcome. Reverse osmosis is very energy intensive, especially when you have water that has as high a salinity as seawater does. So it's used in Israel and other places in the Middle East where they have very little water and they generally have access to a lot of power or energy, right? So, and those are really the only places where it's likely to be a viable technology. In other places that don't have access to that much energy, it's not so good. And there's also other implications to consider associated with use of that much energy to generate drinking water. Greenhouse gas emissions, for example. So there's kind of collateral damage that's associated with this. I mean, it can be done. We know how to do it. There's no doubt about that. And the efficiency of membranes, for example, as a desalination process, reverse osmosis membranes in particular, has improved dramatically. But they're approaching the thermodynamic limit. And I don't think there's anything we can do about going around that problem. So it's one of the tools that are going to be out there, but I don't think it's the only answer. Yeah.
I'll ask one is, as you know, I'm from New Orleans area, and down there they recently found amoebas in the water supply system. Does both of these treatment options typically kill off that?
Yeah, so amoeba are pretty big in the microbial world, and that makes them pretty easy to get rid of, either by physical separation or by some disinfection process. So if we know they're there, I mean, we can go after them. Actually, the project in Las Canas that I talked about a few minutes ago, one of the things about that project that has been really interesting and beneficial for us is that we've interviewed a physician at the local community health clinic there. She actually does diagnostic. 40% of her patients are there because of the water they drink. They're sick. I won't give you more details. So, but she's done actual clinical work to identify the pathogens that are responsible, and amoeba are a big part of her problem that she deals with regularly. Well, now we know to target them, and once we know they're there, they're really pretty easy to go after. They're not really a challenge for us. But knowing that they're there is helpful to us. So I would imagine the same thing would apply in New Orleans. Yeah.
Any other questions?
I have one more answer. Is it possible to change Wabash River into some clean water we can swim?
Yeah, I mean, that's a great question. I think it's a great example. So it's being done, actually. People do use the Wabash River as their source of drinking water, as an example. And if you can drink it, you can probably swim in it. So, I mean, I don't know that I would recommend swimming in the Wabash now, but the technology is definitely out there to take Wabash River and turn it into something that you could be safely immersed in or drink, either one. Yeah, no problem. It's expensive because there's a lot to remove, but you can do it. There's no problem doing it. Yeah. We don't do it here because we have really a great source of groundwater here that's essentially uncontaminated and almost infinite, at least relative to the rate at which we use water. So, yeah.
Another quick question. What, in your long involvement with water management, water resources, water pollution, etc., what do you think that, say, some of the biggest challenges in water area in the world? Now, we obviously read about developing countries, the water, polluted water, they drink the same water they wash in and the waste food.
You've just described what I consider to be the biggest.
That's,
Yeah, I don't think,
be done about it.
I mean, the problems that we have in this country are largely problems of water supply, access to the water. If we can get it, we can clean it up. That's not a problem. But if you go to many developing countries, that's not the issue. They can face both water quantity and quality issue. We focus in my group mostly on the quality issues. That, you know, we work changing the composition of the water to make it safer to drink. And trying to do so in a manner that's consistent with the local economic situation, social, cultural, political issues. But I think that's the most profound problem that we have, is dealing with water in developing countries. I think that's why the UN and NAE have identified this as such a priority. And, you know, really, there's no reason why we can't do this. We know how to treat water. There's no excuse why we can't do this.
And also
So-
a lot of disease, waterborne diseases, a lot of people are become sick and die.
Well, I mean, just as an illustration of that, Kumaris, you know, we don't maybe talk about this as often as maybe we should, but the water treatment profession has eliminated more disease than the medical profession collectively, because diseases like cholera and typhoid in developed countries are virtually non-existent. And there are many other water-related diseases that have been eliminated virtually by the use of water treatment technologies. So, yeah, I mean, we can do a lot, and we know how to do it, so we need to do it.
Well, why not doing it? If we can do it, then why not doing it?
There's a lot of barriers that are out there. So, the barriers that we have to this are largely financial. I mean, the students in this class have done a great job of writing proposals. In fact, their success rate in terms of proposals that they write, the fraction of them that are funded, are higher than anybody I know. But they're writing small proposals. But the funding that they've brought in by writing these proposals is the funding that we're depending on to develop these systems. So that's a slow process. If there were more money that were available to do this sort of thing, we could have a larger impact at a faster rate. And so we're searching for that money. So,
Also, a great extent, cultural problems. Somewhere I read that a great proportion of the pathogenic bacteria, etc., can be gotten rid of by just using simple tools like a few layers of cloth. If they put
Exactly.
people, but so you have to, education, I think, is an issue.
that's a big part of the deal. So that's in part why we're doing this. You know, education, it's not just a question of show up and build a system and then leave. That's a recipe for failure. You're guaranteed to fail if you do that. So we don't want to be adding to the list of failures that are out there.
Well, Chip, thank you so much.
You're welcome.